Hey guys, welcome to Unit 12, Notes A. We're going to learn all about oxidation and reductions today. And they always go together, so we affectionately call that redox. We're going to learn about redox reactions. So as the term might suggest, this happens often with oxygen. I want to kind of look at why. So redox reactions are some reaction where an electron is transferred from one substance to another substance. Or I should say at least one electron. It could be more than one electron. So oxidation and reduction will always have to occur simultaneously. If one substance is gaining an electron, the other substance would need to lose an electron. Because electrons are matter, they are particles, and so conservation of matter would apply. We need to make sure that we're keeping track of these electrons so that we're not writing equations that aren't balanced in the number of electrons. And so to do that, we're going to use something called oxidation numbers. Related to the charges, but just a few more rules to guide the oxidation numbers. So these rules follow something called a hierarchy or an order of importance. So you would follow rule number 1 before you would follow rule number 2, and so on. So the first rule is that if I have an element that's uncombined with other atoms, then the oxidation number is 0. So here are some examples. There's regular metals like sodium or sulfur, nonmetals too, just like solo atoms. Or if they come diatomic, those diatomic versions would also be as an oxidation number of 0. And it doesn't even have to be diatomic. Any set of its own atoms, like carbon can have 60 atoms in one molecule, that would still have an oxidation state of 0, as long as there's not multiple atoms together, like multiple types of atoms together. If you are looking at an ion, the oxidation number is equal to the charge. So for example, magnesium, which has a charge of +2, has an oxidation number of +2. So the charge will dictate the oxidation number. Number 3, the oxidation number for hydrogen is usually +1. There are some times when hydrogen acts a little bit differently, so let's look at a couple of examples here. With sodium hydroxide, the oxygen would have a charge of -2. So my sodium and my hydrogen can each have their charge of +1. Just going back to the idea that charges cancel, these would be our oxidation numbers as well. With sodium attached to the hydrogen here, sodium hydride, the sodium is going to have to be +1. Remember that hydrogen can play the role of a nonmetal, meaning in this situation, it would have to be -1. We wouldn't typically say that hydrogen has a -1 charge, but it can have a -1 oxidation number. In this situation, where it's acting like the nonmetal, the H can be a -1. All right, number 4. The oxidation for fluorine is always -1. Keep in mind that we follow the rules in order though. So if I had diatomic fluorine, that would have an oxidation state of 0. But if you're looking at maybe hydrofluoric acid, +1, -1. So we're able to follow actually rule 3 and 4 at the same time on that one, giving fluorine the -1 oxidation number. The general rule of thumb is the more electronegative atom will end up with the negative oxidation number. Okay. Number 5, and this one's going to come up a lot as we work the problems, the oxidation number for oxygen is usually -2. Now, why usually? Well, let's look at hydrogen peroxide, H2O2. Hydrogen's rule came first. It was rule number 3. So it's going to have to be +1. But I have 2 of them, so I need a total of +2, meaning I need a total of -2 in order for the charges to cancel out. But I have 2 oxygens, so each oxygen would actually have an oxidation number of -1. We wouldn't say it has a charge of -1, we would say it has an oxidation number of -1 in order to get a total oxidation state of 0. So the idea that we still add up to 0 is still going to apply, and it's super important. Where those other rules are guidelines that need to be followed in order, the summation rules will always work. So if you're looking at a neutral compound, the oxidation number should add up to 0, like I just showed with the hydrogen peroxide. If you're dealing with polyatomic ions, the sum of the oxidation numbers should total the overall charge of the atom. Let's look at sulfate, for example. SO4 has a 2 minus charge. So we know that oxygen is supposed to be a -2, and there's 4 of them, so I have a total of -8. This rule says the total oxidation state should be -2. So then what is it that sulfur's oxidation state should be? We would want it to be +6, because +6 minus 8 would equal -2. Adding up to 0 is what we use for neutral molecules. We would add up to the charge for a polyatomic ion. All right, so we're going to use these rules and guidelines to start with what we know. We're going to then work backwards using those summation rules in order to determine the charge for the other elements, like I just did for the sulfur. So let's do a couple of these examples. Let's look at sodium nitrate. First thing I do is spot my polyatomic ion. I know that NO3 should have a -1 charge. That is the charge for nitrate. So I'm going to start with my oxygen, just like I did with the sulfate, and I can see here that I need a total -6. But I want nitrate to end up with a -1 total oxidation state. So what would need to be the oxidation state for nitrogen? +5. +5 minus 6 will equal -1. Therefore, that will be the oxidation states of nitrate, whether it's alone or in a compound. But when I come in and I look at the compound, I need the neutral molecule to add up to 0. So what is it with a +5 and a total of -6 would add up to 0? My sodium would need to be +1. Notice that that's normal when what we get off the periodic table. You're going to see that most atoms will follow that their charge is their oxidation number. We just have to watch out for a few exceptions. So the answer here is +1, +5, and -2. The oxidation number is per atom. Let's look at the SO3 ion. So this is sulfite because it has 1 less oxygen. So I would start with the rule for oxygen having -2, but this time I have a total of 6 negative charges. But remember, when you change to the different types of ions, the charge still stays the same. So sulfite, just like sulfate, has a -2 charge. So then what would sulfur's oxidation state need to be this time? What -6 is going to give me a -2? This time, my sulfur would have an oxidation state of +4. Trying to get the summation rules to work. So the oxidation numbers are +4 and -2. We do it per atom. Let's do one last one. We have hydrogen, carbon, and oxygen. Now we have a rule for hydrogen that it's usually +1, and I do have something negative, so I don't have to worry about it being -1. My oxygen would be a -2. So this one I could actually work without pulling out that polyatomic ion. I can see I have a total +1 on the hydrogen. I need to figure out what carbon will be, and I would have a total here of -6. And this entire ion should have an oxidation state of -1. So what would my carbon need to be in order for the +1 and the -6 to total -1? We would want a +4. 4 + 1 is 5. 5 minus 6 is -1. But let me show you something else. We do have this polyatomic ion here, right? CO3. And carbonate actually had a 2 minus charge when it's on its own. So let's see if we get the same oxidation numbers. Oxygen would be a -2 3 times, so -6 total. And I want my total oxidation state to be -2. So what would carbon's oxidation state need to be? +4. Notice how this matches what I got when I did it in the entire ion. So the polyatomic ion rules will work, their summation rules will work, and the total summation rules should work. So this is going to give you multiple strategies that you can use to solve the problems. All right. So that's our practice on assigning oxidation numbers. What does it all mean? So we're going to go over 4 important definitions. Oxidation is the process of losing electrons. Whenever you lose something negative, you become more positive. And so we would say the oxidation number is increasing. Reduction, on the other hand, would be the process of gaining electrons. And so if you absorb something negative, the oxidation number is going to decrease. We can also refer to the substances causing oxidation or causing reduction as oxidation agents or reduction agents. The catch is the oxidation agent is going to cause oxidation, and therefore it itself would be reduced, whereas the reducing agent would need to cause reduction, and the only way to cause something else to be reduced is to it itself be oxidized. So this can get a little bit tricky. The other thing that you want to watch out for is when I'm talking about agents, like reagents, I want to know the entire chemical. Whereas if I'm talking about what is being oxidized or what is being reduced, I would be talking about an individual atom. So there are a couple memory tricks to help us remember that oxidation is loss and reduction is gain. Starting with oil rig. Oxidation is loss, reduction is gain. You have to be able to keep track of the difference and identify what substance is being oxidized, what substance is being reduced. And to do that, you're going to look at the change in oxidation numbers and determine whether it's a loss or gain of electrons. Another trick is Leo-Ger. So losing electrons would be our oxidation for Leo, and gaining electrons would be our reduction for the Ger. Either way, two acronyms mean or do the same thing, just helping you remember which one's oxidation, which one's reduction. So next thing we're going to do is put this all together and look at a chemical reaction. The first thing we need to determine is whether or not we have a redox reaction. So the redox reaction is going to show a change in oxidation numbers. When you assign the oxidation numbers for an atom on the left and the right, or the reactants and the products, you're going to see different numbers on an individual atom. And that would have to happen to two different atoms so that you can have a gain and a loss. When you see that, you know you have a redox reaction. If all the oxidation numbers stay consistent for an individual atom, it's not a redox reaction. So let's look at an example. The very first thing that we have to do is assign oxidation numbers to every atom in the compound, or in the compounds that are in the reaction. All the atoms up here need oxidation numbers. So let's start with MgCO3. I see the CO3, and I know carbonate has a 2- charge. So starting with oxygen having a -2, a total of -6. I want a total oxidation state of -2. So what would carbon's oxidation state be? It would have to be a +4, and that's going to apply to my molecule as well. +4 and -2. Now let's look at the molecule as a whole. I have what for magnesium? +4, and I would have a total of -6 here in order to get 0, because there is no charge. So what would be my oxidation number for the magnesium? +2, and notice how that matches up with what we would expect from the periodic table. Now let's move on to MgO. Starting with the oxygen for -2, in order for that to cancel out, magnesium would have to be a +2. And over on the carbon dioxide, if I give oxygen a -2, because there's 2 of them, that would total -4. So in order for that to be neutral, what would carbon need to be? +4. So I'm going to clean this up a little bit so that all I'm looking at is my oxidation numbers. Now, is this redox? Do you see a change if you look at magnesium on both sides? No. Carbon on both sides. +4, +4. No change. Oxygen everywhere. -2, -2, -2. No change in oxidation states, and therefore this is not a redox reaction. So we would label it non-redox. Non-redox. No change in oxidation numbers. All right, on to the next one. So let's look at the individual compounds and determine our oxidation numbers. So zinc is a standalone element, and that was our very first rule. So the oxidation state is 0. On to copper sulfate. I'm going to start by pulling out the sulfate, SO4. Notice how copper is a transition metal, so I really have to be able to pull out my polyatomic ions when I'm dealing with them. I know sulfate should have a charge of -2. So if I start with oxygen's -2, I get a total here of -8. I want it to add up to -2. So what would need to be the charge for sulfur? Well, it's going to need to be a +6. So that means it's going to be my charge, or my oxidation state, I should say, in my compounds. So a +6 and a -2. And then I can also apply that to this sulfate, +6 and -2. So now the question is, what is the copper? So if I have something that I need to add to 6 and subtract a total of 8 in order to get no total oxidation state, or an oxidation state of 0 total, what would the copper need to be? A +2. And the same thing's going to happen over here, same exact math, and so zinc also has a +2. And then that leaves copper, which again is standalone, so the oxidation state will be 0. So let me clean this up. So all we're looking at is our oxidation numbers. So I want to compare the oxidation numbers on the left to the oxidation number on the right for each atom. Is there a change first in zinc? I started at 0 and it became a +2. So yes, there's a change in oxidation number. That should always occur in pairs. So what else changes? Well, let's move down to copper. Copper started at +2 and ended up as 0. So that's also a change. So the oxidation and reduction reaction is occurring between the zinc and the copper. If you look at the other atoms, sulfur doesn't change and the oxygen doesn't change. So it's only between the zinc and the copper. So I'm going to go ahead and connect the zinc with a bracket and the copper with a bracket. This is going to start building into our next set of notes for balancing these reactions. In order to go from 0 to +2, I have to have an increase of 2. So I'm going to write the change in oxidation number in the center of the bracket. In order to go from +2 to 0, I would have to decrease the oxidation state by 2. So I'm going to write a -2. That -2 is always going to indicate the reduction, whereas the positive change in oxidation number will always indicate the oxidation. The oxidation number is increasing because the substance is losing electrons. Almost said that backwards. Oxidation is loss, so a loss of electrons would cause an increase in oxidation number. Reduction is gain, and so gaining electrons would make it more negative, and so you see the decrease in oxidation number. The other thing we're going to have to do as we start notes B is to get these numbers to match. They happen to match right now, which means that this is not only a redox reaction, but a balanced redox reaction, which is awesome. In our next set of notes, notes B, we're going to look at how to balance reactions when they don't match the change in oxidation number. So it's going to be Unit 11, Notes B. We'll see you there.